Now it is the second part of section 7.4. Here we'll consider some details for the computation of the kernel PCA. Look at the remark. First, we have to find the eigenvector pairs of the kernel metric K. Now alpha j are normalized. This is usual output from Python eigenvector computation. Now then we may conclude that the first K principal components for the kernel PCA are the collection of that one with scaled by the square root of the eigenvalue. Now, once a point is given, then it can be projected onto the principal components in this way. Now, Zj is phi x transpose Vj. That is now, this is phi transpose t, and Vj can be written in this way. Now we have an extra component. The reason is that, okay, earlier in the first part, once Vj is normalized, then in this connection, if it is normalized to become 1, then length of alpha j must be here 1 over square root of mu j. Now, alpha j is normalized in the software, so that once you are using the output, then you will have to give mathematical scaling here. So that is extra 1 appeared. Now with that here, if we move this one to over there, then we can reach out this expression. Now that one is now phi x transpose, now phi xl. That one is a dot product of the expanded the points. And rather than that, we may use a kernel function such that that portion can be replaced by k. Now there's kernel function xxl. So the kernel function take 2 points as input and try to make a value. So in matrix structure, we can write in this way. Now, along with this one, we can consider kernel trick, and rather than explicit expansion and dot product, we just try to make a value by using a kernel function. That is the basic idea of kernel trick, and we learned it when we study nonlinear support vector machine. The exactly same way, we are using kernel trick. So rather than explicit expansion and now dot product, we try to use a kernel function to get kernel metric. And here, the k, the curly k, is a kernel function you choose. As for nonlinear SVM, you can choose the kernel function from polynomial kernels and hyperbolic kernels, and also Gaussian kernels. The same way you can choose the kernel function. And here at this moment now, we can use a kernel trick. That's the beauty, and rather than explicit expansion, you can finish the computation very effectively. Here, now, in general, phi of xi may not be mean zero mean, so that for the kernel metric, and it better be normalized before starting the finding its eigenvectors and eigenvalues. So here, that normalize the mean zero that data can be gotten from original expanded data and the averaging. Then you can get here normalize the data points, so that here once you are using the kernel, then if you are using that explicit in this way, then here it can be written this way again one more, so that here we make a transpose and the original one normalized, and we expand and we reach at these 4 terms. It can be written in this way. The k tilde, the normalized one, is from original one. We are subtracting 1 over n of k, and then again that is in a sense transpose, so that we multiply the other way, and then now that is 1 over n squared, so that we are multiplying both sides. 1 over n is the n by n metric, having entries all the same as 1 over n. So here this can be realized very quickly, and just one line you can normalize it. Okay, here we summarize the kernel PCA. In the beginning, we pick a kernel function k, and we try to get the kernel metric. Then the kernel metric is may not be here standardized, so we here now normalize it by using this formula, and then now we solve the eigenvalue problem, so that we try to get the eigenvalues and eigenvectors of normalized kernel metric, and eigenvectors are usually normalized. Then here the k principal component for the kernel PCA is obtained in this way, and then for data point, and we can make the principal component by making this product, so that it reach at that one. Okay, now here it's a little bit different format, and earlier look at this cyan colored parts here. Okay, that is along with square root of mu, and we have here 1 over mu, and now, and we put, rather than twice of square root of eigenvalues, we just multiply square root of mu, so that it is changed into the mu1, mu2, and up to mu k, and we eliminated this portion. Then it's simpler. So that is exactly here, this one. There's no mu j involved. Now, rather than the square root of mu j, we are using mu j here. Okay, in this way, you can do it. In the Resca's book, the program is given along with that one. So in standard PCA, there is square root of the eigenvalues, and there's no eigenvalue involved. However, for kernel PCA, you have to consider extra square root of mu j, so that it's changed into now the eigenvalue themselves. So if you consider this one as the singular values, then in fact that one is a singular value squared. Okay. Okay, here with an appropriate choice of kernel function, the kernel PCA can give a good re-encoding of the data, So it'll make a really good transformation. And also, here, kernel matrix is in n by n dimensions. N is the number of data points, so that the kernel PCA will be difficult when we have lots of data points. Number of data points are increasing, then kernel PCA will become more difficult. But anyway, rather than solving in p dimensions, sometimes p is much larger than n, and even p can be infinity, so that it is a way, this kernel PCA is a way of getting here the kernel PCA. Okay, that's the end of section and the end of the chapter. Thank you.